Linear regression is actually an extension of the Pearson product moment correlation. In Chapter 7, I demonstrated how two variables could be described in terms of the strength and the direction of the relationship. Linear regression is the next step after correlation. Linear regression is a statistical procedure used when you want to predict the value of a variable based on the value of another variable. The variable we want to predict is called the dependent or sometimes outcome variable. The variable we're using to predict the other variable's value is called the independent variable or sometimes the predictor variable. So in singular linear regression, we want to describe the relationship between two variables by the calculation of a prediction equation. And this prediction equation averages all prior observed relationships between the two variables. These averages are then used to develop a precise equation to predict unknown values of the dependent variable. And the descriptive word single in singular linear regression refers to the number of the independent variables. So single variable regression is contrasted with multiple regression, where you have two or more independent variables. Multiple regression is discussed later in the semester. After completing this chapter, you will be able to accomplish these learning objectives. Some differences from your textbook will be that we really work on how to interpret the analysis and the output from a single linear regression analysis, and then you will know how to write the results for that linear regression using APA style. Simple linear regression takes correlation's ability to show the strength and direction of an association a step further by allowing a researcher to use a pattern of previously collected data to build a predictive model. Here are some examples of how this can be applied to our disciplines. We might want to just know, does work balance life issues have an impact on extension agents' occupational commitment? Does time spent revising influence the likelihood of obtaining a good exam score? Or does changing a school have an impact on a pupil's educational progress? In the example I'm going to use in the lecture today, we are going to look at a prediction that would involve a manager of a public swimming pool observing a day's temperature and recording the number of patrons at the pool. Several days' temperature could be observed, and then that information could be used to estimate the number of expected patrons for any day's temperature just by looking at the data in an informal way. Well, the SPSS data file I'm going to use has hypothetical data for the number of patrons, which is the dependent variable. We will investigate the relationship between a day's temperature and the number of patrons at the public swimming pool. And we wish to develop a way to estimate the number of the patrons based on the day's temperature. One of the questions I commonly hear from graduate students is, what is the sample size I need to use when running a linear regression? You're going to find a lot of rules of thumb about the sample size needed for linear regression. The two most common being that you should have 10 cases of data for each predictor in the model, or 10 cases of data per predictor. These sample sizes really oversimplify this concept, and we need to dig deeper when deciding what sample size is appropriate for a study. So what I want you to do is to remember that it depends on your effect size that you want and the power we want to detect for the effect size. And so I refer to Cohen's benchmarks, and we want a zero 0.8 as the high level of power to test that model um, being significant. And then for expected effect, we look at 0.02 for small effect size, 0.13 for medium, and 0.26 for large. But a general idea would be if you expect to find a large effect, then a sample size of 77 will always suffice with up to 20 predictors. And then you should always have a sample size above 55, and with 6 or fewer predictors, you're fine with a sample of 100. But of course, Andy Fields always tells you the larger the sample size you have, the better the chances that you'll be able to predict that information without violating any of the assumptions needed. To help you be able to calculate an appropriate sample size, I want to recall a few of the options from Chapter 2. One of my favorite programs to use is G-Power, but you can also use Power and Precision, and then Power Analysis and Sample Size. And knowing whether or not your data can be used appropriately for linear regression, you need to remember that your two variables need to be at a very specific level of measurement. So for your predictor variable, it needs to be continuous or dichotomous. And remember that dichotomous has only two answer choices and is nominal, whereas continuous is on an interval or ratio level of measurement, but that your outcome variable has to be continuous at the interval or ratio level of measurement. There should be no significant outliers in your data set. An outlier is an observed data point that has a dependent variable value that is very different to the value predicted by the regression equation. And as such, an outlier will be a point on a scatter plot that is vertically far away from the regression line, indicating that it has a large residual. And the problem with outliers is that they can have a negative effect on the regression analysis. It actually reduces the fit of the regression equation that is used to predict the value of your dependent or outcome variable based on your independent or predictor variable. This will change the output that SPSS statistics produces, and it reduces the predictive accuracy of your results. So fortunately, when you're using SPSS statistics to run a linear regression in your data, you can easily include the criteria that helps you determine possible outliers. It is recommended that you do a histogram to identify potential outliers, that you can generate a normal probability plot, also known as a PP plot, of the data before applying the outlier test. And then the lower and the upper tails of that normal probability PP plot can help determine whether we need to check for a singular outlier or whether we need to check for multiple outliers. And then lastly, you can run the Kolmogorov-Smirnov test, and just know that your significance value must be greater than 0.05 to have normal distribution in your data set. The other assumptions you need to consider are linearity, homoscedasticity, independence, and normality. So when you choose to analyze your data using linear regression, part of that process involves checking to make sure that your data that you want to analyze can actually be analyzed using linear regression. You need to do this because it is only appropriate to use linear regression if your data passes these assumptions required. It might add a little bit more time to your analysis, requiring you to click a few more buttons in SPSS statistics when you're performing your analysis, and it will make you think a little bit more about your data, but this is not a difficult task. You need to refer back to chapter 5 when we discussed the beast of bias and the way that you would test for data assumptions, because the processes are very similar. So for assumption number 1, we need to worry about additivity and linearity. There is a need to be a linear relationship between your two variables. Whilst there are a number of ways to check whether a linear relationship exists between your two variables, I suggest creating a scatter plot using SPSS where you plot the dependent variable against your independent variable and then visually inspect the scatter plot to check for linearity. You got to look at the scatter plot of the resist RESID plotted against the Z pred, and if it looks like a random array of dots, then it's good. If the dots have a pattern in them, like a curved shape, then this is probably a violation of the assumption of linearity. If the relationship displayed in your scatter plot is not linear, your model is invalid. You can transform your data to make the relationship linear using a strategy from chapter 5. For the next assumption, we want to look at the homogeneity of variance. At each level of the predictor variable, the variance of the residual terms should be constant. That just means that the residuals at each level of the predictor should have the same variance or homoscedasticity. So when the variances are very unequal, they're said to be heteroscedasticity. You need to look at the graph of the Z-res plotted against the Z-pred, and if it looks like it's a random array of dots, then that's good. If the dots seem to be getting more or less spread out over the graph, it looks kind of like a funnel shape, then there's probably a violation of the assumption of homogeneity of variance. If the dots seem to have a pattern, then you'll need to be able to address that. What I suggest doing is rerunning your analysis using weighted least squares regression. That way you do not violate the assumption and your model will not be invalid. Now, if you violate the assumption of independence, you can know this that your confidence interval and your significant test will both be invalid. So to check for independence, you need to look at your PP plot and your scatter plot. But I want to introduce to you something else you can also use to test this assumption. It is the Durbin-Watson test. It is available to you in the statistics menu when you run the linear regression. And I'm going to show you what it looks like in the data set that we're going to use in this example with the pool data. So when I go to analyze this data, I have run all my tests, and now what I have to do is look at the model summary table, and you will see the Durbin-Watson number, and you will know that all of the scores for your independent and your dependent variable or uncorrelated if you have a value of 2. If the value is greater than 2, you have a negative correlation between the adjacent residuals. If you have a value below 2, then you have a positive correlation between the adjacent residuals. And this would indicate, in this situation, that we have no problems with independence. Let's take a look at the other tests. So what you need to do is be able to interpret your p-plot, okay? And so for your p-plot, you can definitely figure out if it fits the assumption of linearity. The fact that you see these really small circles close to the straight line provides evidence that the error terms, that's the difference between your predicted and your observed values, are indeed normally distributed. So if the small circles stray far from the line, then we have to assume nonlinear or non-additivity, and then we have to seek statistical procedures other than linear regression. We can also interpret the scatter plot, and this will help us to be able to look at the assumptions of linearity, homoscedasticity, and independence. And so the scatter plot combines your standardized predicted values, your Z-pred, with the values for the standardized residuals, or the Z-resid. For our regression to be accurate, there must be equal variability in the dependent variable for each level of the independent variable. We see that the small circles are randomly dispersed in this scatter plot with a corresponding lack of pattern. Such an appearance indicates equal variances in the dependent variable for each level of the independent variable. This data characteristic is referred to as homoscedasticity and as a requirement for using linear regression. So we can say that this requirement of linear regression is satisfied and can confidently continue with our regression analysis. Now I want to talk to you about the test for normality. You can look at the histogram and the normal probability plot of your data. Your histogram needs to be symmetrical and approximately bell-shaped. And the normal PP plot will show deviations from normality as deviations from the diagonal line. You can test the distributions for the two variables for normality using the Kolmogorov-Smirnov test. So let's take a look at the data for our scenario that would allow us to predict the number of patrons who will go to a public pool based on the day's temperature. So in our histogram, we see that it's fairly symmetrical and that it does fit a bell curve well enough. I do want to warn you though that distributions can look very non-normal in small samples even when they are normal. So it's important for you to be able to make that judgment call and be able to interpret the histogram and the numbers to decide if you've met the assumption of normality. If you forget the steps for running the Kolmogorov-Smirnov test, this slide includes those steps for running it, and I'm just going to use this in the lecture. I do want you to know that in the Fields tab, you just have to put in the dependent variable and your independent variable in your data set, but that you can follow along and make sure that you have everything done correctly for the process. In the SPSS file saved as swimmers.sav, I am going to now show you how to do the Kolmogorov-Smirnov test. You need to click on Analyze and select Non-Parametric Tests. Click on One Sample. In this tab, you're going to go to the Objective tab, click Customize Analysis, go to Field, and then make sure that the variables temperature for the day and patrons are in the test fields, and if they aren't, you can move them just by clicking on this arrow. Then you click on Settings, and I'm going to make sure that I have customized tests and I am observing the distribution against hypothesized with this test option. Under the Options tab, I want to make sure the Normal tab and the Use a Sample Data is selected for the distribution parameters. I click OK and then I click Run. The data will now appear in the SPSS output, and I will go back to letting you know how to interpret this information. In this slide here, you're going to see just the hypothesis test summary. I've inserted it into the PowerPoint slide, so you have an actual hard copy of it to use. But this significance value of 0.915 and 0.636 are the two values you need to look at. The results of the Kolmogorov-Smirnov test are satisfactory because both of these distributions are determined to be normal, and this is just one of those other times when we do not want to reject the null hypothesis, because the null hypothesis states that the distributions are normal. So we're really hopeful that they do not depart from the normal to a great extent. And in this case, the analysis provided by SPSS has provided us evidence that these variables approximate a normal distribution, and then we can move forward on our regression analysis. Remember that this number has to be greater than 0.05. Now I'm going to show you how to run the linear regression in SPSS. So in your SPSS data file, you're going to go to Analyze, Regression, Linear. Then in this dialog box, my temperature for the day is my independent variable. The patrons attending the pool is a dependent variable. The statistics, I want model fit, R-squared change, estimates. This is where I would click for the Durbin-Watson test. Click continue. For plots, I need to make sure I move my standardized predicted values to the y-axis, and that I take my standardized residuals to the x-axis, and then I will click on normal probability plot and click continue. And for the options, I will make sure I'm using the probability of f and that I'm including the constant in the equation. Now what I do is just click OK. I wait for my output. And what you're going to see will be 5 tables and then 2 charts. And to better analyze this data, I've inserted it into separate PowerPoint slides so you can really easily look at the tables and understand what component of each table you need to focus on for analysis.